Next, we're going to talk about how we can estimate our population parameters, beta 0 and beta 1. And these corresponding estimates, of course, are denoted symbolically by beta hat 0 and beta hat 1. These values that we're going to calculate are based upon our sample. And the way that these estimates are found are through something that's called the least squares method. We'll get into the details why it's called the least squares method in a little bit. But for now, let's look at the actual equations that we can use to come up with beta hat 0 and beta hat 1. So first of all, we'll look at beta hat 1. And to do the calculation, simply use sum over all the observations that are in your sample. So from I equal 1 to n. And each time what you're going to do is you're going to take your xi value. So this is going to be an actual, if we think of it in terms of the high school and college GPA example, this will be one of the high school GPAs. We'll take one of those high school GPAs, subtract off the sample mean of all the high school GPAs, and then we take y sub I, which would be like a college GPA, subtract off the mean from all the college GPAs, and we're going to multiply this xi minus x bar with the yi minus y bar. We're going to do that for every single observation, and then we'll sum it up. That's what this is denoting there. And we divide by the sum of I equal 1 to n of xi minus x bar. Now we square it. Now, through some algebra, you can actually show that this expression there is equal to this expression, where now we take each of the x's times each of its corresponding y's for the same observation, add it up. Then 1 over the sample size n times the sum of all the x's times the sum of all the y's. All that divided by the sum of the x's squared minus 1 over n times the sum of the x's. And notice the square now is outside that sum of the x's. And if you're comfortable with saying the summation is always from I equal 1 to n, meaning every sample value, we can write the expression a little bit more shorthand. Okay, so that's how we get beta hat 1. To get beta hat 0, it's actually pretty easy once you have beta hat 1. So all you need is the sample mean for the y's, subtract off the beta hat 1 that you just calculated, times then now the sample mean for the x's. Now, let's actually apply this. So I have a very simple example here that deals with sales in advertising. Typically, one will think that the more advertising that you do, the larger the sales will be, generally speaking. So we're going to let X be advertising. It's going to be measured in $100,000 units. So if X is equal to 2, that means actually $200,000 worth of advertising. And then Y is going to be our sales units. How much are we selling of a particular product, let's say? And it's going to be measured in 10,000 units. So a Y equal 2 means actually 20,000. And we have a very small sample here, and the reasons being so we can show how we can do these calculations essentially by hand. So maybe let's say 1 year's worth of advertising ended up producing a certain number of sales in its units. So first year, $100,000 of advertising produced 10,000 in sales from the units. The last year, $500,000 in advertising, 40,000 units were sold. At the very bottom of this table, I have the summation symbol. This is to indicate, okay, now we're going to sum across all the rows in the table. And so if I were to sum up all the x's, I get 15. So this would be formally I equal 1 to 5 of x of I. Sum all the y's, I get 10. And if you remember in the equation that we just saw a few minutes ago for beta hat 1, we had to take some x's squared, we had to take some y squared, and we had to take x times y. So what I did was I created additional columns in this table where I take, for example, 2 squared is 4. 2 times 1 is 2. And then at the very bottom, I sum everything up. So now that we have that, we can take these sums and simply put them into the equation for beta hat 1, excuse me, and we get 0.7. So this is our estimated slope for our sample regression model, or what other people might call an estimated regression model, estimated regression equation. Then beta hat 0 is then the sample mean for the y. So we had 10 for the sum. There was 5 of the y, so 10 divided by 5 is 2, minus that beta hat 1 that we just calculated, times the sample mean for the x's. 15 was the sum for the x's, divide by 5, you get 3. And so now my y-intercept is negative 0.1. Thus, my sample regression model can be stated as y hat is equal to negative 0.1 plus 0.7 times x. And so here's a simple scatter plot of the data. And we can see that there tends to be a linear a trend that goes up in the plot in terms of as x increases, y tends to increase as well. So if we were then to plot then the regression model, the sample regression model on the plot, this is what we get. Notice how that line tends to go through the middle of those points. Why that occurs corresponds to what the least squares method does. Again, more on that shortly. But all this equation is that's being plotted is y hat is equal to negative 0.1 plus 0.7 times x. So in a high school algebra class, you'll learn how to actually plot a line like this. So for example, when x is 1, y is 1, y hat would be 0.6. So I just put I put 1 in there. 0.7 times 1, 0.7, minus 0.1 is 0.6. So at 1, here is about 0.6. I do that for other possible values of x, and then simply that allows me then to plot a straight line through those points. Okay, so what does this model then mean for us? That's where we go to this slope. So what this says is for every 1 unit increase in advertising, I'm estimating that y will increase on average by 0.7. So if I ask you to interpret a regression model, this is where you focus on typically. And you can say something like this. Sales volume is estimated to increase by 7,000 units for every $100,000 increase in advertising. Using this model, then we can predict. And we can predict that X values, or in this case advertising values, are not necessarily in our data set too. So for example, let's say a company is interested in figuring out if I were to advertise for $250,000, how much would I estimate my sales to be on average? Well, I put 2.5 into my model, and I get 1.65 out. In other words, 16,500 units. That's my estimated value. That's my y hat. Now, if we actually look at the plot again, let me do some erasing. We can see that this line here is not a doing a perfect job of predicting what the sales were. So we see like a little, you see, error between what was observed 1 year and what would have been predicted. We see a little error here. Well, here we got it right on. We see an error there, and we see an error there. Well, that distance that we're seeing there, that has a name. That's called, in statistics, a residual. The word residual means essentially kind of like what's left over. So after I get my regression model, how far am I off? So it's a measurement of error. Ideally, of course, you would like these errors to be as small as possible. So the closer these points are to the line, essentially the better your model is doing in predicting what the actual value ends up being for y. So this is on page 8. And these residuals, we're going to call them e sub I. So in this case, there's going to be e sub 1, e sub 2, down to e sub 5. And they're simply found by taking your y hat sub I that you get from your model. Oops, actually I did that wrong. Take your y sub I that you observe minus your y hat sub I. So in this particular case, we can see that my point is above the line, so that means my residual will actually be positive. In fact, that residual ends up being actually 0.6. When y was 4, y hat's 3.4. This is all at x equal 5. So my residual is 0.6. Okay. So this is top of page 8. Now, as I said here, we want these residuals to be as small as possible. The smaller they are, in absolute value, say, the better the model is doing in predicting. And there's an interesting little property here with this least squares method that finds the equations for beta hat 0 and beta hat 1. And that is, it tries to draw the line in a way that is through the middle of the points. And since it's going through the middle of the points, then if you were to sum up all the residuals, they end up being 0. So that's kind of cool. Okay, so let's talk about how these equations for beta hat 0 and beta hat 1 come about. I have two separate explanations. The first is an intuitive explanation, and then we'll go into a more mathematical explanation as well. And so the stuff that I do here is in an Excel file, kind of another one of these interactive Excel files called least squares demo.xlsx. And what I have over here is my data with student number. I have the corresponding value of y hat predicted from a model. And then also I have the, excuse me, our observations, subtract off our y hat, in other words, our residuals, but now I'm going to square them so that they're always positive. Okay? And what the least squares method does, actually I maybe jumped ahead there. What the least squares method does, it looks at all these squared residuals for a particular beta hat 0 and a particular beta hat 1. I don't care what they are right now. And what it says is, I want to find the beta hat 0 and beta hat 1 such that the sum of all my squared residuals is as small as possible. In other words, minimize. By doing that, this equation that we get, and if you think of it as a line that you're graphing, it's going to go through the middle of those points, but also it's going to be as close to those points as possible. Because if I come back here, I could draw a line like this as well, come up with the equation. I could still have the sum of all my residuals be 0 in the end, depending upon where I draw it. But that's not a very informative line. Instead, we want a line that makes all these squared residuals that we see here, and this is for the high school and college GPA, we want all those squared residuals to be as small as possible when we sum them all up. Well, what's a name for the sum of squared residuals? Well, it's often referred to as SSE, sum of squares for error. Okay? And what one could do is actually use calculus, and we'll see this in a little bit. Use calculus to find these equations for beta hat 0 and beta hat 1 that minimizes the sum of squared errors. But first, before we do that, let's look at then this interactive demonstration. Okay, so we have our data. We already saw that. The least squares estimates, meaning the beta hat 0, the beta hat 1, are shown here in black. The sum of squared errors is 2.1262. This is the smallest possible value that it can occur for any value for beta hat 0 and beta hat 1. Not necessarily the least squares estimate. This is the smallest value. And we can see how, and we have a scatter plot of the data again. So the points in blue are representing our observations. We have this line here that goes through the middle of the points and nicely shows then this trend that we have between high school and college GPA. Now over here on the left side of this table, I have what's called user-provided intercept and slope. So let's say that you just chose a beta hat 0 and beta hat 1, not necessarily using our equations that we've seen. And you want to graph what that line would look like. Well, right now I have it set up to be exactly the same as the least squares estimate. Note that this SSE that we have there is based upon this beta hat 0 and beta hat 1. But let's say, and this is on page 8, let's say I change the slope to 1. Look what happens to the line. Is that a good estimate then of the relationship between high school and college GPA? No, it's not. Look at the sum of squared errors. It has really went up. Okay, so we wouldn't want to use that line to describe the relationship between high school and college GPA. And as I see here, I think, well, maybe I should make it a little bit lower. So how about we put, let's see, which one did I do next? How about we do 0.9? Well, that's looking a little bit lower. And look at that SSE. It has also decreased now to 16.66. How about we make it a little bit lower than that? Okay, now we're getting better. Look at that SSE has decreased. And if I keep on going down, we see we keep on, in terms of the line, keep on going down. We're getting a better description of this relationship with the line. Suppose I go down to 0.6. Okay, well that looks pretty good. And look at how that SSE is fairly close to the best possible, the smallest possible value there. Suppose I keep on going lower. Oh, now my SSE is going up again. And if I keep on doing this, my SSE keeps on going up. So what this little description or this little demonstration shows you is that if you put in these results from the least squares method, this equation that we saw for beta hat 0 and beta hat 1, calculate with your sample, you are going to find essentially the best way to estimate the relationship that you see in a scatter plot like this. And this is for then any data set. So I encourage you to play around with these red colored cells here. See what happens. See what happens to SSE. And you're never going to come up with a better, a smaller SSE for any other value of beta hat 0 and beta hat 1 that you put in there. Okay. Let me jump back over here. Okay. So that was the intuitive explanation of how the least squares estimates come about. These beta hat 0 and beta hat 1. Here is a mathematical description. I'm not going to go through the details because this does involve calculus. So I'm not going to ask you a question on the test to actually derive it as I do here. But real briefly, here's my SSE. And so again, it's the sum of the y's minus y hat squared. And if I put in what y hat is in terms of our beta hat 0 and beta hat 1, this is what it looks like. And so what I'm going to do is take the partial derivative of SSE with respect to beta 0. I'm going to take the partial derivative with respect to beta 1 or beta hat 1, okay, of SSE. Set these equal to 0. Solve for beta hat 0. Solve for beta hat 1. Get those results. And if you want, and those are going to be your least squares estimates. That's what's going to minimize SSE. And there's an additional check that you might have learned, for example, in a Calc 3 class, where you could actually check, did I just find the minimum of SSE or the maximum of SSE based upon what this derivative gave me, setting everything equal to 0, solving for beta hat 0 and beta hat 1. Okay. If you're interested, here's the actual details of doing all the derivatives. Okay. Now let's actually move on to doing the calculations in R. In pretty much all situations in this class, we will use R to do the math for us to calculate beta hat 0 and beta hat 1. You're still responsible to understand how to do the calculation by hand for a very small data set. I sometimes will put a question on the test like that, just to make sure that you understand what these expressions, these formulas actually represent. Okay, so my data is in gpa.csv. I can read it into R. This is what I have. I can do a scatter plot like I've done many times before in this class. Why don't we go ahead and review this? So my x argument says what goes on my x-axis. I'm going to extract out high school GPA from the GPA data frame. My y argument says what goes on my y-axis. So I'm going to extract out college.gpa from the GPA data frame. Put a nice little label on my x-axis, a label on my y-axis, a nice title on my plot. I'm going to control my x-axis limits to be between 0 and 4.5. Same with the y-axis limits. The color of the plotting point is going to be red. I'm going to use a plotting character, PCH, that's equal to 1. This gives me an open dot. CEX equal 1. That corresponds to I want the plotting points to be essentially the default value. So I don't, in terms of the size, so I didn't really need CEX equal 1 there. If I did CEX equal 2, the plotting points would be 2 times as large as normal. And then panel.first says before you actually plot any points, let's put some grid lines on the plot. We're going to color them gray, and we're going to make the line type a dotted line. Okay, so here's our plot. Again, we can see that we have this nice relationship between high school and college GPA. We want to find a line that goes through the middle of those points. To do that, let me actually jump on over here to R. To do this then, we can use a function in R called LM for linear model. We have a formula argument. That formula argument is written in the same way as we've seen in other situations, where my y value is going to be on the left side of my tilde. And I'm going to say that my y is now dependent upon my high school GPA. So I put hs.gpa there. My data is in GPA itself. So if I were to run this, I'm just going to come back over here to Word because I'm going to write on my screen. So if I run this, I put it into an object called mod.fit for model fit. And if I just type model fit, this is what we get. My beta hat 0 is labeled as the intercept. My beta hat 1, which is my slope, is labeled as hs.gpa because it's a coefficient, you could say, on high school GPA in our model. So with that then, I can write out then formulate what my sample regression model is. Y hat is equal to 1.09 plus 0.61 times x, where I actually define what y is and what x is. You need to do that. You don't need this part there. I just did it for emphasis to say, here's what beta hat 0 is, here's what beta hat 1 is. Now, if you want to, you can actually state the model, you can say a little bit less formally, where instead of having x here, we put actually high school GPA. Instead of having y here, we have college GPA. But don't forget the hat. If you write out an equation without the hat like that, you will have points deducted, unfortunately, because it is different from the actual value of y. This is the estimated value of y now. Okay. Now, you might be thinking, okay, that's all that LM did. It just gave us beta hat 0 and beta hat 1. But actually, it did a whole lot of other calculations too. And inside of mod.fit, we can actually look in there. Mod.fit is actually, in R's terminology, a list. And we can always look inside of a list and get a set of names in terms of what's actually in there. And so notice you see one name called coefficients. So if I extract out coefficients from mod.fit, guess what I get? Beta hat 0, beta hat 1 once again. Look at, I have something called residuals. So if I extract out residuals from mod.fit, what do I get? I get my residuals. So E sub 1 is 0.15. This is the distance that the first college GPA, let's call it Y1, is from its corresponding estimated value, Y hat 1. Now what we can do, and there's a whole lot of other things in there too, such as this fitted dot values. This actually gives me my Y hats. A lot of other things there that are not relevant, at least in our course, is also in mod.fit. So what we can do is actually put all this information that I pointed out here into a new data frame so we can see it nicely. So data.frame, I put in my GPA data set, and then I'm going to also put in all my Y hats, my college GPA hats. And the way I'm going to do that is extract out the fitted dot values from mod.fit. I'm going to nicely round them to 2 decimal places. And simply inside of my data.frame itself, I'm going to give it all a nice name. Also, I'm going to do the same thing with my residuals and give it a nice name called residuals. So I put that into an object called save.fit. And here's using the head of save.fit. So for example, for this residual here, that's equal to 3.1 minus 2.95. How does this 2.95 come about? Let me come down here. It comes about through using our estimated regression equation. So it's y hat is equal to, let me get it in my notes here, 1.09 plus 0.61 times 3.04. If you do the math, you get 2.95. So this is a nice little data frame summary of what's going on. But we can also summarize everything that's in mod.fit through using the summary function. We've seen that a number of times before, that this is what this function is nicely can do with particular kinds of objects. And so if I say summary parentheses mod.fit, or more formally summary object equal mod.fit, this is what I get. I get information about the actual call to the LM function, which could be useful for the reproducibility of results. I get a summary of my residuals. And then I have a table called coefficients. And here's our beta hat 0. Here's our beta hat 1. That's located in the estimate column. We have some other stuff in this table that we will talk about as we go along through the rest of this section. Now, also there's a bunch of other things too that we will get to as we go along. Okay. So you know, we've seen this summary function a number of times in our course. We've used it with like data frames before. And the output that it gives from a data frame is different from the output that we just got here. Well, why does that happen? The answer will be given soon. Okay, so now let's actually do a plot of our data with our model on it. So this is a scatter plot with the sample regression model on it. So I'm going to use exactly the same code that we saw before for the scatter plot. Now to get the actual model on the plot, I go back to this function that we've used many times before, the curve function. And remember what the curve function allows you to do. It allows you to create a plot as a function of an x variable. In other words, what's on your x-axis. Well, again, our model is y hat is equal to 1.09 plus 0.61 times x. So what I could do in my expression argument here, or EXPR, I could put 1.09 plus 0.61 times x, and I could get R to actually draw the plot. A little bit more general way to do it is to remember that this coefficients component of mod.fit actually contains beta hat 0. The first component does. So how about I say, let's extract out that first component. Plus, well, what's the slope? Well, remember, it's in coefficients. It's the second component take it times x. Then, well, what range do I want to plot this line? Well, let's start at the minimum of the high school GPAs and go all the way up to the maximum of the high school GPAs, because that's where we've observed information from the minimum to the maximum with respect to the high school GPAs. More on that shortly too. Let's make it the color blue. I want to add it to the current plot. The line width thickness is going to be 2 times the default. And I'm going to use an n equal 1,000 argument there. And what that says is, or tells R to do, find 1,000 equally spaced points from this minimum high school GPA to the maximum high school GPA. 1,000 different x values, equally spaced. Put them into this equation that's in the exp argument, find what the corresponding result is, and then plot it. In terms of plot the corresponding x and y pairs, draw the line that connects them. I use, the default is I think n equal 101, and sometimes that gives a kind of almost like a little bit of a jagged line to it. And so this is what we get then for our plot. Notice how, again, that line goes nicely through the middle of the points. It nicely approximates the relationship between high school and college GPA. Now, lastly here, something that's very important, and that is we don't want to extrapolate beyond the range of the data when we estimate expected value of y. In other words, come up with y hat. So in our data set itself, somehow we have a high school GPA of 1.98 for a student, and it goes all the way up to a high school GPA of 4.32 in our data set. This is the range of the x values for which we can estimate the y at. We have no idea, though, what is really going to happen outside this range. Now, we kind of do because we're familiar with GPAs. But who knows? Maybe for those students who are extremely good, they take a lot of AP courses in high school, and those who, and that's how they get that above a 4.0 GPA, maybe for those students instead, if we were to extend things out, the college GPAs go down. We don't know if that happens. Well, we're pretty sure it doesn't happen, but we don't know. So always keep your estimates for y, or expected value of y, within the range of what you have information on. In this case, the minimum high school GPA all the way up to the maximum high school GPA that we have in our sample itself. So don't extrapolate beyond the range of the data, the range of your the sample information. Okay, so that's an introduction to the least squares method and how we can actually do these calculations in R to get beta hat 0 and beta hat 1.